Okay, let's recap how to solve second-order linear differential equations that have got constant coefficients. So the general form of such an equation is this yellow expression here. So we've got a second derivative, that's what makes it second order. We've got a first derivative term multiplied by a constant coefficient, so a is just a number here, just a coefficient. B similarly is just some real number multiplying y. And then on the right hand side we've got this function which is just a function of the independent variable x. So this function of x is what we've been calling the forcing term, or the right hand side term. So we said in the lectures that the general solution of any linear ordinary differential equation is of this form here. So the solution is the sum of two bits really. One is the complementary function and one is called the particular integral, and we're going to denote those yc and yp respectively. In terms of what those actually are, well, the complementary function yc is just the general solution to this differential equation here, which is exactly the same as the yellow equation at the top, except we've replaced f of x with 0. So this is the so-called homogeneous equation, because we've got a 0 right hand side. So yc is the general solution to the homogeneous problem, and yp is any solution of the original problem. So that's with the forcing term. So the presence of this forcing term is going to influence the particular integral, but it's not going to influence the complementary function. In order to solve one of these second-order linear differential equations that's got constant coefficients, it's therefore a kind of two-step process. First of all, find the complementary function, yc, and then you find the particular integral yp. So let's start off by considering how to find this complementary function, first of all. Now, in order to do that, we consider the so-called auxiliary equation, which is this equation here, m squared plus am plus b equals 0. And the way that we get that equation is that we look at our original second order ODE and we replace the second derivatives with m squared, so this d2y by dx squared becomes m squared. We replace first derivatives with m, so that's a times m comes from here, and then the term just in the dependent variable y without derivative, we replace y with just 1, so this is b times 1, so that gives us this b here. And then, as we said, with the complementary function, we're not bothered about this forcing term, so we just have 0 on the right hand side. So our auxiliary equation is m squared plus am plus b equals 0. So this is a quadratic equation, and we know from algebra that quadratic equations either have got distinct real roots, let's call them m1 and m2, so there's going to be two roots because it's a quadratic, so they can be distinct, or they could be repeated, in other words we have the same root twice, or they can be complex conjugates, so in other words we can split them into their real and imaginary parts and write that one of the roots will be some number alpha, which is a real number, plus I times another real number beta, or the complex conjugate of that, so m2 is alpha minus I beta. So those are our options. We get different forms of the complementary function depending on which of these three cases we're in. So first of all, let's look at what happens if we have distinct real roots to our auxiliary equation. In that case, then the complementary function is given by this so-called linear combination of exponentials. So in other words, we have some arbitrary constant a multiplied by e to the m1 times x, where m1 is the root of this, well, one of the roots of this auxiliary equation, plus another arbitrary constant b times e to the m2x, where m2 is the other root. So we've got two exponentials, two arbitrary constants in front of them, and it's the sum of those. That's the complementary solution when we have distinct real roots of the auxiliary equation. Now, if we have repeated roots, in other words m1 is equal to m2, then the complementary function is ax plus b multiplied by e to the m1x. So a and b here again are arbitrary constants, and e to the m1x is the exponential that we multiply by ax plus b. Note that We could also have e to the m2x here, because m1 and m2 are exactly the same thing. And then in the remaining case, when we have complex conjugate roots, the complementary function is given by e to the alpha x, where alpha is the real part of both of the roots, and then that exponential is multiplying this whole bracket here. So it's a linear combination of sines and cosines, where beta is the imaginary part, or the size of the imaginary part of each of the two roots. So we have an arbitrary constant multiplied by cos beta x, plus another arbitrary constant, b times sine beta x. So to recap how to get the complementary function, you look at your original equation, mainly at the left-hand side, turn that into an auxiliary equation, solve that using whichever method you want. So you could factorise it, you could complete the square, you could use the quadratic formula, and you'll have one of these three cases. And depending on whether you have distinct real roots, repeated roots, or complex conjugate roots, tells you what form the complementary function will take. Okay, so that's how to find the complementary function. What about the other bit, the particular integral? Well, the method that we use is called the method of undetermined coefficients. And the idea of that, as is written here, is that you make a kind of educated guess of what form the particular integral is going to be in. That will have some arbitrary constant in, or maybe more than one arbitrary constant, and then you substitute that into the differential equation, and you compare coefficients of different types of term. So the relatively tricky bit of this whole procedure is choosing this trial function, making this educated guess of what the form of the particular integral might be. And the general idea is that the choice that we make of what trial function to give a go is influenced by what the forcing term f of x is. So broadly speaking, and we'll see detail in a second, if f of x is an exponential, we'll try some kind of exponential. If f of x is some kind of sines and cosines, we'll try some kind of sines and cosines. If f of x is a polynomial, we'll try some kind of polynomial. But there's also some subtleties, because the trial function mustn't be of the same form as any term in the complementary function. So yes, the trial function is mainly influenced by the form of the forcing term, but also you've got to bear in mind what the complementary function looks like, because you don't want to end up trying terms that you've already got in your complementary function. Okay, so here come the details of what kind of trial function you should choose for different types of forcing term. So if your forcing term is an exponential, let's say e to the kx, k is just some number here, so it might be e to the 2x, e to the 3x, or so on, then you'd seek a particular integral in this form here. So your particular integral would be something like an arbitrary constant multiplied by e to the kx. And then this is arbitrary to start with, this constant a, but when you substitute it into the equation and compare coefficients, you're trying to find out what this number a is. Okay, what if your forcing term is something like a number multiplied by sine beta x, so alpha sine beta x, or maybe f of x equal to alpha cos beta x? If you've got either of those, then you look for the particular integral in this form here. So a sine beta x plus b cos beta x, where these a's and b's are arbitrary constants that you're going to find by substituting this into the original equation. Okay, so if you've just got sine or you've just got cos, you've got to have both sine and cos in your trial function. And then finally, what if you've got a polynomial? So if you've got something like some constant alpha multiplied by x to the power n as your forcing term, then you try a polynomial of degree n. So for instance, if this was alpha x squared was your forcing term, then you'd look for a particular integral of the form of some constant plus some other constant times x plus some other constant times x squared, and then you'd stop if this was squared. If this was cubed, you'd then go up to a cubic term, and so on. Okay, let's run through a specific example of finding the complementary function and the particular integral for a particular differential equation. So here we've got the equation, d2y by dx squared minus 3 dy by dx plus 2y equals 7 e to the 3x. Okay, so the first step is to find the complementary function. So in order to do that, we write down the auxiliary equation. So the second derivatives become m squareds. So we've got an m squared term minus 3 times m, because the first derivatives become m, plus 2 times y. So y just becomes the constant term, so this is plus 2 equals 0. So our auxiliary equation is m squared minus 3m plus 2 equals 0. Now we can factorise that, because this is nothing more than m minus 1 times m minus 2 equals 0, and therefore our two roots are going to be m1 is equal to 1, m2 is equal to 2. And these are distinct, i.e. different, real roots. So our complementary function is going to be this linear combination of exponentials where a and b are arbitrary constants. So the complementary function is a e to the 1 times x, because we've got this, this 1 here, plus b e to the 2 times x, because our other root was 2. So that's the complementary function. What about the particular integral? Well, that choice is mainly going to be inspired by looking at this right-hand side of the original equation. So we've got some constant, okay, it's 7 in this case, multiplied by e to the 3x. So based on what we said on the last slide, we're going to try an exponential. So we'll have a times e to the 3x as our trial function to try and find the particular integral. So our guess, if you like, our trial function is that the particular integral will look something like a e to the 3x, and we're now going to try and find what this constant a actually is. Now the way that we actually do that is to take our trial function, a e to the 3x, and we're going to substitute it into star. Now in order to do that, we know what y is, because it's going to be like a e to the 3x, but what about the derivative and the second derivative? So we should compute those first. So first of all, if we differentiate a e to the 3x with respect to x, a 3 comes in front, so we get 3a e to the 3x. And similarly, if we then differentiate that again, we get the second derivative, so that's going to be 3 times 3 times a e to the 3x, in other words 9a e to the 3x. Now if we substitute that into the equation I've labelled star up here, the original equation, then what do we have? Well, d2y by dx squared we said was going to be 9a e to the 3x, so that's where this comes from, minus 3 lots of dy by dx, so that's minus 3 lots of 3a e to the 3x, so that's minus 9a e to the 3x. And then we've got plus 2y, so that's going to be plus 2a e to the 3x, so that's this term here. And then the right hand side, we haven't got any y's, so we haven't got anything to substitute, so that stays as 7e to the 3x. Now there's going to be some cancellation on this left hand side, because 9a e to the 3x minus 9a e to the 3x, they cancel each other out. So we're left with 2a times e to the 3x is equal to 7e to the 3x. So this is where we compare coefficients. So we say that how many lots of e to the 3x have we got on the left? Well, we've got 2a lots. How many have we got on the right? Well, we've got 7 lots of e to the 3x. So in order for this to be satisfied, this constant a, which appeared in our choice of a particular integral trial function, should satisfy this. So in other words, a is going to be equal to 7 over 2. And therefore we found the particular integral. The particular integral is 7 over 2 times e to the 3x. And therefore the general solution is the sum of the complementary function, which was a e to the x plus b e to the 2x, and then we add on the particular integral, 7 over 2 e to the 3x. Okay, so in this particular example it was easy to guess our trial function, because we had this e to the 3x on the right hand side of the equation, so we could just choose a constant times e to the 3x. And remember we said that we didn't want our choice of particular integral to include anything that was in the complementary function. So in the complementary function we had an e to the x, we had e to the 2x, we didn't have anything like e to the 3x, so this was simple. But then the next question is, what can we do if we do have some overlap between what we'd normally pick for our particular integral and the complementary function? So here's an example where that's the case. So let's start off by just having a look at this and having a think what we might expect to choose as our particular integral. So we've got 7e to the x as the forcing term here. So we'd probably expect to pick something like a e to the x, using our kind of normal rules, our normal educated guess. So we'll kind of have that in mind as we go forward. So if we start solving this, then as we've done in the previous examples, the first thing to do is to get the complementary function. And to get that, we first of all consider the auxiliary equation. So in fact, this is exactly the same left-hand side as what we just had in the previous example. So we've got roots of the auxiliary equation of 1 and 2. And therefore the complementary function is yc equals a e to the x plus b e to the 2x. But then if we recall what the complementary function is the solution of, then it's this equation here. It's the homogeneous equation with 0 on the right hand side. So in other words, if we put in y is equal to a constant times e to the x, or y is equal to a constant times e to the 2x into the left hand side, we're going to get 0. We're not going to get 7e to the x. So that tells us that there's no point in us trying a particular integral trial function of a e to the x, because we've already got something that looks like a constant times e to the x in the complementary function. That's not going to give us a right hand side of 7e to the x, no matter what we choose a as. When we substitute it into the left hand side, we're always going to get 0. So what you do in this situation is you multiply the normal trial function, a e to the x, by x. Okay, so instead of using the trial function of a e to the x, we'd use a x e to the x instead. Okay, let's look at another example. So same forcing term, 7e to the x. So again, we'd probably expect that we're going to be using a trial function that's something like a e to the x. But let's consider the complementary function. So first of all, the auxiliary equation is m squared minus 2m plus 1, m squared minus 2m plus 1 equals 0. You can factorise that. It's m minus 1 squared equals 0. And so that's going to tell us that our two roots are both 1. We've got a repeated root in this case. Therefore, our complementary function is of this form here. So ax plus b multiplying e to the power 1x, because 1 was the root in our auxiliary equation that was repeated. And so what can we try as our trial function? Well, the answer is we try some constant a times x squared e to the x. So we initially thought we'd choose something like a e to the x. But then it's in our complementary function, because if we set capital B to be little a here and capital A to be 0, then we'd have exactly that, a complementary function of this form. So we said before that multiplying by x was normally a good idea. So what if we tried a x e to the x like we did in the previous example? Well, that's no good either, because we've already got terms like x e to the x multiplied by a constant here. That's in the complementary function, and therefore that solves the homogeneous equation where if you substitute it into the equation you get 0, and 0 is not 7e to the x, so that's not going to be any good. So you have to multiply by x squared, multiply the normal trial function by x squared if you have a repeated root. So the kind of rule to take away from this is that if the normal choice of trial function appears in the complementary function, multiply your trial function by x. But if it appears as a repeated root in the auxiliary equation, multiply by x squared. Finally, let's consider what happens when the forcing term isn't something as nice as just an exponential or a sine or a cosine or a polynomial. What if that forcing term is the sum of different types of function, or the product of different types of function? Well, the rules here are actually quite easy. If the forcing term is the sum of the different types of function, for instance an exponential and a sine, then you'd use the sum of the usual types of trial function as the trial function. Here's an example of that. So in this case we've got a forcing term that is the sum of a couple of functions. The first one is a polynomial, a polynomial of degree 2, so 5x squared. Second one is a sine term. So if we just had the 5x squared, we'd use something like a plus bx plus cx squared. Whereas if we just had the 3 sine x as our forcing term, we'd have some constant. I've called it m because we've already used a, b and c. So we'd have some constant multiplied by sine x plus some constant multiplied by cos x. Okay, so we've just added the two trial functions together when we've got the sum of two different types of function as our forcing term. And finally, what if we haven't got the sum, but instead we've got a forcing term that's the product of different types of function? Well, fairly intuitively, you use the product of the usual types of trial function as the trial function. So here's a final example. So on the right hand side, we've got x squared multiplied by an exponential e to the 5x. And so normally for just the x squared bit, we'd use a plus bx plus cx squared as our trial function, and then we'd multiply by e to the 5x. And of course, in both of these examples, you should first of all check that the trial functions don't duplicate anything that we've already got in the complementary functions. And finally, having chosen the trial functions for the particular integral, what you would do in order to get the solution to the differential equation is to substitute the form of the particular integral into the original differential equations and then compare coefficients of terms you've got on the left hand side and on the right hand side. So for instance, with this top one, you'd have some expression involving a, b, c, m and n on the left hand side, and you'd check that the coefficients of x squared on both sides should be equal to 5, the coefficient in front of any sine x terms should be 3, the coefficient in terms of any cos x terms should be 0, and so on. So you just equate the coefficients.